Hello and welcome back to Calculus 2. We are starting chapter 8 on sequences and series. I am going to combine sections 8.1 and 8.2 into a single lecture, to combine them together because they both have sequences as a topic. And whatever part of the series is in there, going to kick that out and add that to 8.3. So all of the material that is covered in 8.1, 8.2, and 8.3 will be covered, but not necessarily in that order. I like to separate the two worlds because they are separate worlds. So we learn sequences first, and then for the rest of the semester, rest of the chapter, 8.2, 3, 4, and 8.3, 8.4, 8.5, and 6, we learn series. So we start with the definition, which I might put on a test for you to state, where sequence is the ordered list of numbers. So I don't want to go and say set, because the set could be set of elements where you can put people and elephants and trees and desks. This is a list of numbers. It is strict. It is a set, but the elements must be numbers. And the very important word is the word ordered. So you can't put whatever in there. There has to be some kind of order. Ordering is achieved through set of counting numbers. Natural numbers n with added 0 in the mix. So whole numbers. So order is achieved through n equals 0, 1, 2, 3, 4, 5, 6, and so on. So a set of counting numbers with 0 added. We do not count, right, 0. Because you don't count 0, 1, 2, 3, 4. You just go 1, 2, 3, 4, 5. So counting numbers and natural numbers do not contain 0, but at our list we are going to add 0 in. So now let's talk about the sequence examples. I can come up with a sequence. Oh, let me just give a notation first. So notation would be AN or BN or CN, whatever. So notation is AN, and that's going to be equal to the list of values for going forever. So now as the example, I can say that AN is equal to, and then I can give you 3n minus 1. So this is a sequence. And you can write the elements of this sequence when you start using n equals 0. So that's negative 1. N equals 1, we get 2. N equals 2, we get 5. And then we keep adding 3 technically to these guys because that's how it worked out. So you can compute all of these values. So your A0 was computed when n was 0. Your A1 was computed when n was 1. Your A2 was computed when n was 2. And so on. So you can compute this list. If you have the explicit formula given, 3n minus 1, you can compute the list of n0, n1, n2, and so on. So all you need to do is to replace the values from the index into n and get the list.
3n minus 1 is what is called the sequence.
Yes. So this is the sequence. This is the list of that sequence. This is the name. Like, you know, we use f of x. Now we use an.
Just to clarify, n cannot be a negative number, right? Since it's only list of common real.
Very good. Yes. And you can never have fractions and decimals in between because counting is done, right? When I walk in, I go 1, 2, 3, 4, 5. I'm not going to go 1, 2, 3 pi, right? Because pi, you ended up being pi.
I guess having like a fraction would be pointless since you have an infinite number of countable numbers, so you technically won't run out of.
Well, these are discrete chunks, so we move in the units of 1. Again, you have 1, 2, 3 trees. You don't have 1, 2, 3.7 trees. So that's one of the pet peeves for statistics. So compute how many babies this year, right? Oh, approximately 7.83 babies. Really? It's discrete. Some data sets are discrete, which means they depend on the inputs to be 1, 2, 3, 4, 5, 6, 7. Brian, you had something? Or? So for the sequence, very simple, very straightforward in my opinion. AN, we can use BN now, okay, for the next one. Here, BN, whatever. BN is n squared minus 2. So compute first 5 terms. I want the first 5 terms of n squared minus 2. What's the first term? Negative 2. Great. Go on. What is the sequence of the first 5? Four squared 16 minus 1, 2, 3, 4, 5, 6. Overachievers, okay. N equals 0, so you get 0 squared. 0 minus 2 is negative 2. Then you have 1 squared, which is 1 minus 2 is negative 1. 2 squared is 4 minus 2 is 2. 9 and 14, 16 and so on. So it works. It works. Now what's important is to understand that this is going to go to infinity. So this list is infinite list. And this here lists the actual bnth term. Now, what's before bnth term and what's after bnth term? Yes? N minus 1 and n plus 1. Very good. So if we are starting an sequence from 0 to infinity, meaning you start counting at 0 and you go all the way to infinity, we are going to encounter A0, A1, A2, A3, dot, dot, dot. And then here are the ones that I mentioned. So an minus 1, an, an plus 1, dot, 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 and it goes forever. Yeah, I wish I want to squeeze this all in one line, so I'm going to, so I'm going to get rid of the A3 term. I'm going to put equal here. Oh, come on. Oh no. Yeah, go do that in your notebook. So this guy over here is known as the previous term. This is the nth term. This is the next term. So we can always say next term is an plus 1. Previous term, an minus 1. So we need those concepts.
So that's like that whole list there is like saying f of 0, f of 1, f of 2. If they were like, if we were comparing them to like function.
Nope. These are numbers. Function represents collection of numbers because function is a curve. Each one of these is a single number. If you want the analog to the function would be this one because it's related to collection of numbers, but it's special. Okay? So if you are right, you would call this a function. F of x equals 3x minus 1, right? So this one is analogous to your f of x. Not these guys. These guys, collection of your y values. Yeah.
What about these y functions? Would it be an infinite amount of these y functions?
We can do that as well. Not yet though, but yes. All right, so definition of a sequence. All right.
There is no previous term for the start of the sequence, right?
No, yes, that's good. Yeah.
Okay.
No previous term. And there's also no last term, right? Because it goes to infinity.
Yeah. Okay.
Right. Now, we are going to define what we call recurrence relation. Recurrence relation is the one that uses the current term and maybe previous and the next term, or few previous terms or few next terms, to create new terms. So recurrence relations define new terms in respect to old terms, right? So they use the new terms to create, sorry, they use old terms to create new terms. So recurrence relations, we can say in parentheses here, uses old terms to create new terms. A quick example. So an is equal to 2an minus 1 plus 4. And we have to define a0 in this case. Otherwise, we can't do anything. So a0 we can pick any value here. So give me whatever value is not going to be crazy to compute. 5 it is.
One quick question though. Is that a n minus 1 or is that very unsigned?
This one? This is an index.
Okay.
You know how you write H2O?
Yeah.
That's how you write it.
Okay, so the 2 and the a are together. Okay.
Oh yes, 2 times. Yes.
Times that, okay.
Yep. So now, to write this list, we start with A0 term, which is given to us, which is 5. That's given, right? And now you can use that term to generate the next term. Yes.
So A0, you're saying it's like A initial, like it's where you
Very good.
where you want to start.
That's where the universe. That's the Big Bang for this sequence.
So once you have like
Then the previous terms are forfeit. So we have A0 term given, and then we go with the A1. You can always shift the counter. We'll talk about that as well. So whenever you start your sequence with A2, I go and I shift the counter. I shift whatever you started with n equals to 2, I renormalize it and I put it back to 0.
and then put A equals 0 minus 5.
So now, the next term, so as you can see, this one and this one are 1 unit apart.
Yeah.
So now, what is A1? A1 is 2, A1 minus 1 plus 4, which is 2A0 plus 4, right? Realize that this n and this n have to be the same value all the time. If you want to calculate A1, which is the next term, you will plug n equals to 1, but you have to plug that n equals to 1 everywhere in the equation. So that's why I get this 1 minus 1 here, because n is 1 now.
So why did you get the 1 on the other side?
This one? Because I'm looking for the next term. I already have A0 term,
Gotcha. Okay.
and now I want to compute A1, A2, A3, A4, A5. So, but observe that this calculation is no longer dependent on n, it's dependent on the entire answer from the previous term. So, what is an minus 1? It's A0, and how much is A0? 5, so, which is 14. Bueno. Move to the next term. The next term is 32. Beautiful. The next term, 68. Perfect. The next term, 140. Yeah, just keep like this.
2 times initial one.
This is more. You can use the previous term to calculate the next term. You can, let's do another example. An plus 1 is equal to an minus 2, an minus 1. Wow, this one depends on previous 2 terms, which means that I have to give you 2 initial terms to start off this mess. So let's start with A0, you like 5, and A1 to be 3, whatever. Right? So start there. So now, if you are writing your sequence, you are starting with 5 and then 3. Those are A0 and A1. They are given to you. You have to put them there. So here's your A0 and here's your A1. Now what's A2? Well, this needs to be now A2. Now this is a little bit tricky. Pay attention. If this needs to be A2, what n am I using?
1.
N is equal to 1. Very good. So n equals to 1 because, you see, I'm aiming for A2. Well, that means n plus 1 is 2, which means n is 1. So what are these n's then? This is A1 minus 2 A0. Perfect, I have both of those. A1 is 5 minus 2 times 3, and the whole thingy is negative 1. No but, that's it. Oh, details. Negative 7, right?
Yeah.
Great. So now you just go and use the next term. N equals to 2. If it's n equals to 2, when you plug in n everywhere, n equals to 2, you get A3 is A2 minus 2A1. You have the values for A2 and A1. A2 is negative 7, right? You see that A2 is negative 7. And minus 2 times A0, sorry, A1, which is 2 times 3. So this is negative. Very good. One more. N equals to 3 gives us A4. Because again, when I plug in n equals to 3 in the original equation here, 3 plus 1 is 4. So I get that equal to A3 minus A2. We know 2A2, sorry. So A3, we know it's that negative 13 minus 2 times, and A2 is negative 7. Ooh. Do we all have positive 1?
Yeah.
Let's calculate. Calculate. I can't even speak. Calculate one more. N equals to 4. So that's going to give us A5, which is A4 minus 2A3. See you next week. Which is equal to 1. Minus 2 times A3. No. Yeah, I'm negative 13 over here. And all together is 27. And it goes forever. Close the brace. When the problem says 5, you do 5. First 5 terms. In this case, we calculated first 6 terms. What happened?
You're saying it's not that bad.
No, it's not. Because it's called an intro. Eventually it grows into this.
I need to be scared. Yeah. Oh yeah, it's scared.
No, wait. Oh, I missed the section, sorry. There it is.
Oh my god. Oh. Hey. Oh my god.
You see the recurrence relation? And then it looks like this. And then you do this stuff to come up with this. Oh, this is a section differential equations. 3-2. I know. But there are steps, guys. We start with the basic thing and you spend hours working on the basic thing, and then we upgrade into the next level. We are not going to slam you immediately with a differential equation, recurrence equation, and then you go and work with that. We start with these things, right? I'm going to ask you now to write down Fibonacci sequence. And other things, yep. Rabbits too.
You know when you're recording a video,
Mhm.
and there is this window that shows that you're recording the video. You know what I'm talking about?
Mhm.
There is the Fibonacci sequence in there too, because it's the window recording the window recording the window.
Oh yeah,
Yeah, I was looking at that just today, and look at that.
this one.
Wow.
Yeah.
Isn't it?
Yes. Fibonacci sequence. Do you know what Fibonacci sequence is? Every sequence goes. What is the rule to create Fibonacci sequence? What do? Add two previous terms. I want you to write the formula for that and and what are the first two terms? 1 and 1. Fibonacci sequence starts with 1 and 1, which is male and female rabbit. And then it models that population. The population growth. All right, let's go. That's it. I'm giving you a verbal assignment right now. Write out the Fibonacci sequence and with F and 2 B's.
Oh, 2 B's.
Predicting our grades.
What?
I said I was predicting our grades. I have 2 B's.
Oh, F and 2 B's? All right, fine. So Fibonacci sequence, it's going to start with 1, 1. I am challenging you to write out the formula. It's a recurrence relation where the new term depends on adding previous two terms. You might have different answers for the formula, but that's okay. What? Oh my God, you and your spelling. So the rule is that you have to add two old terms to create a new term. So add two old terms to get the new term. Maybe these quotation marks are not necessary. There we go. So add two old terms to get the new term. And we start with A0 equals 1 and A1 equals 1. Now, to write the sequence, since you know the rule, you don't need a formula for it. You just use common sense because you have the first two terms and a statement. So you start with 1, 1, and it says to create a new term, add the previous two old terms. So 1 plus 1 is? 1 plus 2 is? 2 plus 3 is? 3 plus 5 is? 5 plus 8 is? 8 plus 13 is? Yes, very good. Yeah, you're losing the interest, I see. Now, what's the formula?
A n plus 1 is equal to a n minus 1 is a n.
Good. Here's the new term. And this is the sum of two old terms. Is this the only way to write this? Hell no, right? You can write this any way you want. You can write it as an plus 2 is equal to an plus 1 plus an. That's also three consecutive terms, right? You add the values of the an and an plus 1. Right? There are many ways in which you can write this out. They're all valid. So now you know how to deal with sequence.
Yeah.
I actually caught up to that guy who drives the moped because he said he goes to Somerville.
Is he still driving the moped?
Yeah.
That's what I'm wondering.
Yeah.
All right, good. Yes. We.
So 1 plus 1 is 2.
It's a pattern. Now, let's graph these. Graphs of sequences. So, let's start with the simplest. Well, that's not a simplest sequence. The simplest sequence probably just equal to 1. You know that your input are all counting numbers. N. And for every n you pick, the value an is 1. So what you get is this constant stream of ones like this. It's 1 for a0 as well. An equal n. Again, your an, you can think of it as the function goes on y, and the n is the input. So now, we have 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, so on. We don't connect them. We just leave them. This is the discrete set of data. Remember that 1.7 doesn't exist in this universe. There is 1, and then there is 2, and nothing in between. So the space in between remains empty. Recall that your y equal x graph was, boom, 45-degree line through the origin. It does contain points 1, 1, 2, 2, 3, 3, but it contains also half, half, 3 halves, 3 halves, 3 quarters, 3 quarters, and so on. Yes?
What if you have a sequence to where like an is equal to an over 2? Then you would have a fraction, right? Or an plus 1 all over 2, or something like that.
You are okay to have answers to be fractions. Your input is always n. The domain is the one that, right? Your domain is the set of counting numbers, and you can't have fraction there. Well, since the popular demand, Bn is equal to 3 halves n minus 1. So negative 1. The first dot is at negative 1. Where's the next dot? Three halves? No. 1 half. It's 1 half. So why is it 1 half? Because when you plug in 1, you have 3 halves minus 1. That's 3 halves minus 2 halves, which is 1 half. How about 2? Add 2. How about 3? Very good. How about 4? Excellent. You see the linear behavior because the 3/2 n minus 1 resembles 3/2 x minus 1, which is the linear line. If I replace bn with y and n with x, I get to draw the straight line through this. Can I? Yeah.
Is there a situation where there would be 3/2 n squared minus 1?
Could be. Why not?
Okay.
Well, the next example is actually addressing your question, but it actually extends it further. Let's go with Cn is equal to 2 times the square root of n plus 1. Can we have this? Yeah, we can. We can make graph, yes.
Professor, for every problem, you want me to graph it?
If it says graph, graph. If it doesn't say graph,
Or you just do
then you graph it because you love it. So what do we have? You can make the chart of values if that makes you happy. And Cn. So for 0, you get 2. For 1, you get 2 root 2. For 2, you get 2 root 3. For 3, we get 4. For 4, we get 2 root 5. And so on. They're not necessarily nicest things to graph. So we can pick on those values that are cool. So 0, 2, and then 1, 2, 3, 4, or 1, 2, 3, 1, 2, 3, 4. The next nice value over here would be what? Very good. Which gives us? Perfect. So 1, 2, 3, 4, 5, 6, 7, 8. And we go 6. Right on this line. That's what it is.
Draw a line.
Hmm?
Draw a line.
Nice.
Like begs you.
I know.
Begging you.
No, I'm just making sure you're paying attention.
Then you connect the dots.
Conditioned.
Connect the dots.
Yes. Well,
The system has failed me.
the system has failed you. There are dots there. All right, one more. Well, maybe we can do 2. I know how much you love this stuff, so. How about an is equal to 1 over n? What's the graph for that one?
It looks like that.
Yes.
Except without the negative.
No,
What?
it doesn't look like this. It looks like this.
Okay. Yeah. Without a negative sign.
these kind of motions are now non-existent.
Now we're going to create a table. Right?
It's not a ballet now, it's now step dancing.
You just chose
Skiing,
0,
skiing.
1.
Or not,
Skiing?
ice skating.
Oh, dude, this is so easy.
No, step dancing.
Can't start off with
No, no,
zero.
no.
Oh, shit, man.
From smooth lines. Ice
So
skating.
then what do we do?
Oh, okay.
Then you have to start off with clockwise.
So what do we have when we pick n? Can we pick n to be 0 now? No.
Oh, so if it makes sense to find, then you can't use it.
Very good. And what I'm going to do is to restart. There we go. Can't do 0. Yeah, it's still syncing. Oh, it's synced. Okay. I'm going to pick now four units to be 1. And on the x-axis, maybe 2 units to be. So I have 1, 1. I have 2 and 1/2. I have 1/3. And 1/4.
Is this where you would take a limit since it goes to infinity?
I made a mistake there.
Even so that's not even the graph, you don't write it down.
What happened?
You don't write zero even though it doesn't appear.
Well, this is, I'm not sure what you mean. You don't connect the line. You don't do this. We can add 1/5 if you want to.
Would you write it limit as n goes to 0?
Nope.
No?
Infinity.
So, functions asymptotes. What about
They have bounds.
bounds?
Bounded. All right. So now, guys, look at this. What do I see over here? This one tends to stay at the level 1 forever as n goes to infinity. This one and the next one and the next one all go to infinity. They all go to infinity as you let n to go to infinity. And the last one here, as you let n go to infinity, an goes to what value? 0. So over here we can say, oops, limit as n goes to infinity of an is equal to the limit of 1 over n as n goes to infinity, which is 0. We can go back and do the same thing for all others. Limit n goes to infinity of Cn is the limit of 2 times the square root of n plus 1 as n goes to infinity. Now you see that when you plug in infinity and add 1 and take the square root, you still have infinity times 2, still infinity. Problems which go to infinity, we say diverges. And that is the word that we are going to use every time. That means it diverges from being a number, like 7. So it diverges from being any particular value. Come on. There we go. So we say diverges. What I usually do is D in a bubble.
Like how we were doing the integrals in the last chapter, is there
Yes, it's the same concept as the integrals that you did in the last chapter when they can converge or diverge. If you have an answer, numerical answer, like we have 0 in this case, we will say converges to 0, converges to pi, converges to 3. Right? It's going to converge to a value. For convergence, we use C in a bubble. I mean V. Right? So I use this because it's shorter than writing converges and diverges every single time. What this limit shows is that the sequence is either going to diverge or converge. Divergent sequences go to infinity, and we might not be able to use them for our application. Convergent sequences converge to a final value, which we can. If you're thinking about any kind of physical reality, we deal with finite values. You don't deal with infinite. You don't. You walk into this room and what do you have? A finite number of chairs, a finite volume, a finite amount of air, a finite number of lumens of light. Everything that you see around you is finite. Everything. Everything you see over here is finite. So we, in sciences and design and engineering, we are interested in these infinite sequences to produce finite values. Because if you are trying to store infinite amount of energy into your battery for a cell phone, what do you get? Boom. Exactly. You get Samsung 7. So, or Sony laptop from years ago. So you are not trying to pack infinity into finite container. So we always use this test for sequences, and if depending on what kind of answer we get, sequence might be useful to us, might not be useful to us. So now, are you ready for a little bit of red and pink? Test for convergence of sequences. And it simply says limit of an as n goes to infinity is either L, which means finite, which gives us convergence, or is infinity, infinite, which gives us divergence. That's your first one, guys. 10 to go. But it's the only one for sequences. Sequences have only one test, and series have 10. So that's it. If you are testing sequence for convergence or divergence, all you need to do is to take the limit of that sequence as n goes to infinity. Now, let your imagination go and figure out what types of limits you will be taking. 1 over n? Not so much. Something that uses L'Hopital rule on half a page? Most likely, right? So, please review L'Hopital rule so that you can take all of the limits that are coming up in this section. So sequence either converges or diverges. You can't have both. They're mutually exclusive. Two sides of the same coin, right? One or the other. At this point, note that there is a procedure here. You have a sequence. You need to know that you're supposed to take the limit. You're supposed to solve the limit. You're supposed to know that if you get a finite number, it's a finite value which is convergent. If you get infinity, positive or negative, it's infinite, it's divergent. So you have to know a lot of these things. And all of those steps are part of the grade. Note that the final answer is either C or D. It's a 50-50 guess, right? That means that if I put more than 30 problems on the test, if you just guess all of them, you'll have about 50 on the test, right? Plus 7 quizzes. Because L, a limit, finite value, like we had 0 above. So having the correct C or D circled brings you 2 out of 8 or 2 out of 10 points for the problem, because that's the finite answer. The rest is procedure, stating and using right methods, and calculations, algebraic manipulation, and all the other stuff brings the rest of the points. So answering the question, just, you have a problem, and then there's half a page blank, and you just put C in a circle, and you guess it right. Congratulations, but it's 2 out of 10 or 2 out of 8. But you still got it, so you should be proud. We have a little bit more work on sequences, and then we are done. We have limit laws, and we have vocabulary about monotonic sequences, decreasing, decreasing, non-decreasing, non-increasing, and all of that kind of stuff. And I believe then we're done with sequences. So we are now going to write the limit laws, which are the same as limit laws in limit laws. Number 1. Limit of an plus minus bn as n goes to infinity is going to be the sum or difference of their limits. All right, so the limit of the two sequences an and bn, whether they're added or subtracted, is going to be addition or subtraction of their limits. 2. If you multiply by a constant, that constant can go in front, and it's just CA. Same thing like the derivatives and integrals. You kick the constant outside. And 2 that you don't have for limits and integrals. You remember this? It doesn't work for derivatives, doesn't work for integrals, but it works for limits. And the quotient as well. So we don't need any special formulas. But we have to state that Bn is different than 0, and B is also different than 0. Great. Those are the limit laws. Say your sequence an is given as 3n squared minus 3 over n squared. You want to calculate convergence or divergence on this one. You will take the limit of n goes to infinity of 3n squared minus 3 over n squared. And you know by this rule here, right, rule number 1 for addition and subtraction, that you can deal with the two functions that you guys have on a pile. You can deal with those functions separately. So the limit of 3n squared as n goes to infinity is infinity. And then 3 over n is, if n is infinity, 0. So infinity minus 0 is infinity, and this one diverges.
Real quick. So, in A n and 3n squared, how did you give us that?
Yes, that's the problem.
So, okay. And the
So
answer would just be
the entire problem, test for convergence.
okay. And then my answer would be
Problem is divergent because you have infinity minus 0, which is infinity, which is divergent.
gotcha.
One more. So Bn is equal to 1 plus 1 over n to the n. What? What?
And now you basically revert that.
Your question?
I have an answer.
Right, sure.
You have an answer? This one really got me
Can't do that because you have exponents. So those rules. What do you do without rules? Yeah.
That's when you keep going until I got it right. I know.
You're done.
Yeah.
That was really easy.
Was it?
Yeah, didn't you pick
Perfect.
Oh, I didn't think any of that. Yeah.
Tied onto like your butt, like your board across, like wrapping around.
Maybe one. Maybe it's not that one. Maybe you're not.
That's where the weekend goes. That's where the weekend goes.
My weekends are gone.
So the answer is converges to E. Very good. Because the limit over there is the limit definition for E. Now you're supposed to know that from Calc 1, but also you're supposed to know this from 6.8 from this class. If you flip through your notes, I defined E using this limit. Shall I flip? Because I know I'm not trustworthy. There it is. In blue. So the only test that we have for convergence and divergence of sequences is to do the limit. Limit n goes to infinity of 1 plus 1 over n to the n, and then just because you're alive and you're in calculus, you should know it's E. Therefore converges because that E is the finite value. Now say that you never learned that. Your option is L'Hopital rule. And the L'Hopital rule says to solve the limit, right? Or we say y equals 1 plus 1 over n to the n. And then we ln both sides, because that's the only way to peel off the exponent. Oh, hold on. Where's my limit? Limit 1 plus 1 over n to the n. There we go. Much better. So now this n goes in front of ln. The limit n goes to infinity and ln swap this. They can swap because of the ln is the increasing function. So ln y is equal to the limit n goes to infinity n ln 1 over plus 1 over n. So the exponent jumps in front, but then we also swapped ln and limit, so we have this. Now when you test plug in infinity, you get infinity times 0. Right? You get infinity times 0 because this is 1 over n is 1 over infinity, which is 0. 0 plus 1 is 1. ln of 1 is 0. So now, if you have this form of infinity, maybe I should use that. Let me use purple rather than red because we have a lot of reds. If you have infinity times 0, we use the trick that f is equal to 1 over f. And that will change it in the form where we can use L'Hopital's rule. So ln y is equal to limit n goes to infinity, and now ln 1 plus 1 over n divided by 1 over n. And now what we have is 0 over 0. And that is indeterminate form, so we can finally use L'Hopital's rule, and L'Hopital's rule says take the derivative of numerator and denominator independently. The derivative in denominator is much easier than the one on the numerator, so I'm just going to do that one first. So it's negative 1 divided by n squared. And now the derivative up there. Remember, ln, you write the argument as is. And then you put the derivative up, which is negative 1 over n squared. So now you can deal with the double fraction or whatever you want, in any way you want. What I'm going to do is I'm going to take negative 1 over n squared divided by 1 plus 1 over n and multiply that by negative n squared over 1, which is the flip of the denominator, right? And now we see that these guys cancel. And we are left with ln y is equal to limit n goes to infinity, and over here these guys cancel, you are left with 1 over 1 plus 1 over n, which is 1. So we have ln y is equal to 1. We e both sides to get rid of ln, and there it is, y equals e. And remember that y was defined as the entire limit. So limit 1 plus 1 over n to the n is e. Oh, you're going to memorize it now? Awesome. It's so easy to convince you. I just solved the example once, and I don't have to worry about it anymore. I am going to enhance this formula. Limit 1 plus a over n to bn as n goes to infinity is going to be e to the ab. Now, those of you who like the proofs and things, you are going to solve this, obviously, using the same methods as I used above, where b and a are constant numbers, right? Whatever. A can be 3 and b can be 10, and then 3 times 10 is 30. Yes. Yes. Yeah, that's 4.7. L'Hopital's rule, or 4.8, whatever is the, yeah, Calc 1. So that's the trick to transform infinity times 0 into 0 over 0. Because all I did is I took this n and I wrote it as 1 over n. Over here? Oh, up. You mean this one? Well, that's the formula that I showed. And then I did the calculation, and we got the same thing. So you either remember the formula, which is this one, or you do the procedure for L'Hopital rule. Yes?
If we were to graph this y equals e as a function, I'm sorry, not the y equals e, but the previous one that we started with, you can see that the y value would start with,
No, it will go up.
I'm sorry, would converge to e.
Yes.
Correct? And it would be horizontal then.
Yes. So the graph would look like this.
Yes. Yeah.
It will be n, and it would go, and it would, yeah.
What does this tell us about growth?
About what?
Because e is the number of natural growth, correct?
Could be growth of anything. Guys,
Why is this significant at that point?
well, it's not saying it turned out to be the model, the solution to the differential equation that models these kind of things, but the e is significant for other reason, which is what we covered in 6.8, where the integral cuts off the area and so on. So E is not important because we found an application for it. E is important, and then it fits the application. Right, a little bit. All right, we have a few more rules to write out, and we are done with this section. I just need to find, there it is. I wish I just crop and paste this into the tablet so I don't have to write it, but well, let's do it. Terminology for sequences. So terminology for sequences. Sequence AN is increasing if AN plus 1 is larger than AN. This simply tells us that the next term is bigger than the previous. Right? AN is non-decreasing. Uh-huh. And now you have the equal sign. See? The non-decreasing is combination of a constant and increasing, right? You have three concepts. Decrease, increase, and constant, right? Our first example, AN equals 1 was constant. Flat. Would you call that one increasing?
No.
Decreasing? No, right? So you can't call that one increasing or decreasing. That one is constant. So now, the sequence is called increasing if the next term, you see plus 1, next term is bigger than the previous term. It's called non-decreasing if the next term is larger or equal to the last term. So that one allows for repeats. You can have a sequence that goes 1, 1, 3, 3, 5, 5, 7, 7, 9, 9, right? 11, 11. That is non-decreasing because it has the other two features. So you say non-decreasing because you are excluding the only one that it's not on the pile. Sequence 1, 1, 3, 3, 5, 5, 7, 7, and 9, 9 is ordered. And you also see that it's increasing, but it's also constant because you have 1, 1. And then you have 3, 3. You have 5, 5. So constant portion is there, increased portion is there. The only one that it's missing is the decrease. So it's easier for us to say non-decreasing rather than bring in the other two terms. Yes?
I think it was like maybe a third example that we did. There went like.
They can be neither.
But can it be both? So it can be both though. So you're only looking at the sequence in only certain portions, or just the two numbers that you're looking at. Because like one of the other examples that we did, it went from where it went 5, 3, 7, or -7, -13. So it's going both ways. So
Exactly. It's not going to be anything on our list.
it won't be anything on it.
Yes.
Okay. So it has to be the whole sequence, not just a portion.
Exactly.
Okay.
Or the portion of the sequence that you're observing.
Okay.
Yes.
What about a sequence that is all 1, 1, 1, 1, infinity? Is that a non-decreasing as well? So
Yes. Yes. But we are going to say that that's monotonic. That's next part. So function is sequence is increasing, non-decreasing, and then it's decreasing if the next term is less than AN. And then we have is non-increasing if AN plus 1 is less than equal than AN. Then we have AN is monotonic if it is either non-decreasing or non-increasing. And finally, bounds. Sequence N is bounded if there is a number m such that the sequence is smaller than that m. So all these are words. You have increased, decreased, non-increased, non-decreased, monotonic, and bounded. Yes?
For monotonic, it doesn't necessarily mean that an plus 1 equals an.
That's actually what it means, because it is the one that, who mentioned, 1, 1, 1, right? 1, 1, 1, 1, 1 is monotonic.
Okay, so that's
Would be that one. It's a constant as well. It would be that one. You can't exclude equal sign. I gotta go over there. Next time, get up and scroll. The bound, yes, that's I just have to scroll now. Make sure it works.
Wait, so can monotonic be anything else but that?
Monotonic means that it doesn't change the direction. That's what monotonic means. So it can go, it can be flat, it can go again, flat, go up. If it starts going up at one point, it can never go down. That's what monotonic means. It means it either goes up or it goes down. It might flatten a little bit.
So, and I guess in that case, then it must be easy to do a convergence or divergence for monotonic, because it would always converge to that same number, right?
But it's not only constant ones.
Okay.
Every single one except that one that fluctuated, which we had, was monotonic.
Okay.
Because they were always decreasing, always increasing, which is non-decreasing, non-increasing at the same time. And or constant. Only one example was that we had 2 negative, 2 positive, and then 2 negative again, and then a positive. So that one is definitely not monotonic because it goes up and down, like sine curve, not monotonic because it goes up, down, up, down, up, down. The quadratic function, not monotonic. It goes down, goes up. But linear function, every single linear function is monotonic. Every single, well, x cubed is, but x cubed minus x is not, because it has the bumps like that.
So what do we label the one that has 2 negatives, 2 positives, 2 negatives?
Neither. Yeah, we don't use these names to describe it.
Okay.
We can call it evil. We need to talk about the bound. Yes.
I was just wondering about the monotonic because you're saying it can change, so it can be like flat for a long time and then it can jump to another point.
No, it has to, if it starts increasing, then you can have flatten, and then it has to increase again and flat and increase forever, for instance. That's monotonic, because you always see the trend of increase. This is not monotonic, because there was this part here which was decrease, and everything else was increase. So monotonic means it does the same boring thing for the rest of its life.
Then maybe the an equals an plus 1 is not the best way to put it.
No. The bound. You can think of the bound as the horizontal asymptote. You can think of a bound as the horizontal asymptote. So, if I put a bound here, which is m, I might have some kind of sequence that is going to follow, and over here I will say an is bounded by m, and you can say from above. And then you can have situation like our dear friend inverse tangent. You have inverse tangent of n. Well, that one is bounded from above and below. You are going to have these dots like this. You are not going to have a straight line. But you see that there are M1 and M2 bounds. And they're both pi over 2, right? Negative pi over 2 on the bottom and pi over 2 on top. So now we know what the bounds are, right? Which are the asymptotes in this case. So that's about the bound. And I think the rest we're going to talk about sequences. The squeeze theorem works the same way that the squeeze theorem works for limits.
For the tangent, inverse tangent, and do you have that negative?
No.
Okay.
Can't have a negative part for the, because you go with the n minus 1, so kill it. Oh, you're using pens? Don't.
So would that mean that it's bounded by 0 also?
What happened?
Does that mean that it's also bounded by 0? Oh wait, no. Never mind.
Yeah, actually it is bounded by 0.
Oh, it is.
Because it doesn't go past it. If you want to think about it, it can produce two bounds, and the domain is from negative infinity, from 0 to pi over 2. Domain at the range. All right, squeeze theorem, and we are done with sequences. Then we can take a break. Oh no, you have the growth rate, right? Growth rate. You better be growth rate here.
Yeah, we do.
Good. So squeeze theorem. Says let AN, BN, CN be sequences with AN less than BN less equal than CN for all N and then we write our statement. So if limit AN is the same as the limit of Cn as n goes to infinity, and then that's equal to some value L, then limit of the one that is squeezed in between has to have that same L value. Identical theorem to what you learned earlier in Calc 1. I like to call this sandwich theorem. Many textbooks are using sandwich theorem. Need another piece of bread. So here we go. Bread, cheese, and bread. If you're lactose intolerant, put full slice. It makes you strong. The one that is badly behaved is in the middle. The one on top and one on the bottom are the ones that are easy to handle. So now, whatever the values are for the top and the bottom is the value for the one that is squeezed in between. Now, in our sandwich analogy means wherever I pick up the sandwich and I grab it by the bread, wherever I place that, the cheese goes with it. right? So whatever bread does, whatever is sandwiched in between has to do the same thing, right? So that's how this works. You have a badly behaved sequence Bn, which, you know, taking the limit is just insanity. But then you have a nicely behaved An and Cn, which squeeze. That one, you find those limits. If those limits end up to be 2, then the limit for the one that is squeezed in between has to be 2 as well. That's the entire squeeze theorem, which is exactly the same as Calculus 1.1. There's nothing there. And they give us the nice example, Bn equals to cosine n over n squared plus 1. Now you're going to say, oh, you cosine n. If I plug in n that goes to infinity, what is cosine of infinity? Now, you know that the cosine is bounded between -1 and 1, but you don't know which out of infinitely many values that you have between -1 and 1 is the answer as n goes to infinity. So taking this limit is not nice. But what we can do is we can construct easy functions to take the limits. So you start with the notion that cosine n is bounded by 1. And that gets us to write 1 less equal than cosine n less equal than positive 1. Now you compare the function in the middle with the function that you have in the problem, and you immediately realize that what's missing is this denominator of n squared plus 1. Now you can't divide just one side, you have to divide all 3 sides, so n squared plus 1 and n squared plus 1. Now you see that the one in the middle is exactly the same as the one that we had for the function, but we also have these 2 squeeze functions, right, to the left and to the right, sequences. Oh, come on. So now you take the limit everywhere as n goes to infinity. So limit of -1 n squared plus 1 is equal to 0, because you're dividing -1 by infinity. And also limit of +1 n squared plus 1 as n goes to infinity is also 0. So now when you combine the two, since this one is squeezed in between, this limit, without actually solving the particular limit, right? Just because it was squeezed in between, that one must be 0 as well. Yes. So taking these limits, you know, might become a challenge. So what we do is we learn about growth rate of functions. Sense the tone. Growth rate of sequences. So growth rate of sequences, and we have a roadmap for that. The sequence ln raised to some power of q grows slower than the polynomial 1 n raised to any power grows slower than the multiplication of the 2 grows slower than multiplication of 2 polynomials when you add their exponents, which grows slower than the exponential one, which grows slower than the new one you haven't probably seen yet, the factorial one, which grows slower than the boss, n to the n. Just to get some sense for this, we create a chart of values. Here's your vanilla n, 0, 1, 2, 3, 4, 5. And over here we can put n squared. We can put 2 to the n. We can put, what else do I need? Oh, I skipped 2n. There we go. 2n, n squared, 2 to the n, n factorial, and n to the n. This one. Oh, polynomial. So both of these, all three of these are polynomials, actually. All right, so 2n. Double everything. All right, we see the growth, right? But then let's see n squared. Do we all agree that it grows faster? It actually starts slower and then picks up. We all see that, right? It starts slower pace. It doesn't get to 2, it starts at 1, but then quickly catches up and beats it. How about 2 to the n? Very good. We have to wait for this growth. Oh yeah. I'm not paying attention. So 2 to the 0 is 1, 2 to the 1 is 2, 2 squared is 4, 2 cubed is 8, 2 to the 4 16, 2 to the 5 32. We see that this one is definitely faster than both of the previous ones. And now we get to n factorial. Do you know what the n factorials are?
You multiply it from the n all the way to 1.
1, yes. So this notation, which is read n factorial. This is not read n. This is read n factorial. All right. You have to be cool about these things. So n factorial is 1 times 2 times 3 times 4 times ... n minus 2 times n minus 1 times n. And that's it. That's right. So n factorial is going to multiply these. So and 0 factorial is 1, 1 factorial is 1, 2 factorial is 2 times 1, which is 2, and so on. So 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, and 24, and then 120. Look at that growth, right? It starts by losing, right? Starts by losing to all of the previous ones, right? But then when it picks up, it takes off quickly. And finally, the boss. 0 to 0 is? Yes, okay. And then 1 to 1 is 1, and 2 squared is? And then 3 cubed is? And then 4th to the 4th? 256. And 5 times 5, 3,000. 3,125. Look at that one. That one goes whee. There is a proof for that, and I can show it if you're interested after the. But just
Not just math, right?
well, no, it is math.
Of course.
The same deal. What is 0 to any exponent here? What is 0 raised to, what's 0 squared? Because 0 times 0 is 0. What's 0 to the 7th power? 0, right? So these guys tend to be 0. What's 1 to any power? 1, right? Now, what's any number raised to 0? 1. Now, do you see this one and this one, and you combine them together and you get 0 to 0 actually equals 1? I know. And you use limit. You can prove this to table of values. You have to use limit, use the table of values, and you prove this here. You take 0.2, 0.1, 0.05, 0.07, 0.0, right? And the closer you're getting to 0, this will be going to 1. So instead of reasoning with this every single time, we designated some storage space for it, and then we don't have to worry about it. So the factorial of 1, and sorry, factorial of 0 factorial is going to be equal to 1. 1 factorial is equal to 1. You designated some storage space for that, and you move on with your life. How do you use growth rate? No, you have limit, n goes to infinity, and I'll say slow over fast. That one works out to be 0. And the limit of fast over slow is infinity. You are not going to be able to use your beloved L'Hopital rule when you run into a problem which has factorial in it. So if I have a problem where an is equal to n squared minus 1 over n factorial, and I want to check the convergence or divergence of that particular sequence, can't do any of the methods that we know. But you already said it's 0. Why? Because it's slow divided by fast, and this is slower and this is faster. That's what I mean. One is going to be slow, one is going to be fast when you compare the two, because they're somewhere on the spectrum, right? So you are going to immediately say, yep, 0, convergence, done, right? Now that problem cannot be done in any other way, so learn that logs are sluggish, then polynomials, then exponential, then after exponential you have the factorial, and then the boss, n to the n. That's fusing together the exponential and polynomial ones, right? You know that the difference, if you are, you just stare and you realize stuff, right? And then you have the boss. So you have the polynomial ones, you have exponential ones, and then you have the fusion of the two. That one is the one from the last column that just took off extremely quickly.
I can make a very nice philosophical argument about that also.
Go ahead.
We're talking about
No, I'm saying, no, oh, this tricky, okay. That's it for the lecture. We're gonna stop here, and then the break, come back, series. What's the argument?
well,